Okay, YouTube, in this video we're going to continue our exploration of solving polynomial equations, but we're going to introduce ourselves to what we call the Descartes rule of signs. Okay, and so Descartes is named after this gentleman here, Rene Descartes, same gentleman who we named the xy coordinate plane after. We call it the Cartesian coordinate plane. But what he did was he noticed that there's a relationship between the coefficients of a polynomial function and the number of possible positive and negative zeros of that function. So however many possible positive or negative zeros is related to the signs of the coefficients. So that's why we call it Descartes' rule of signs. And I'm going to take you through what it says here first before we put it into practice, but it's a pretty easy thing to use. We say if f of x is this polynomial, this long polynomial written in standard form, and we have degree n and leading coefficient a sub n, we would say as long as this is a polynomial function with real coefficients, then the number of possible positive real zeros of f is actually equal to the number of changes in sign of the coefficients of f of x, or is less than that by an even number. So to show you what is meant by this, what we're going to look at up here is basically these two examples. It says determine the possible numbers of positive real zeros and negative real zeros. And I'm going to neglect this for now. I don't really care about the imaginaries, just possible positive and negative. So what this says is, for f of x, it's the number of changes or variation in signs of the coefficient. So when we write this out here, I say f of x, I guess I'm rewriting the exact same thing. It's not like I'm doing anything impressive here, but I get this. And what we're looking at is, as we look left to right, how many variations in SIGN sign occur amongst the leading coefficients. So I say I go from a positive to a positive, and what I notice is going from a positive to a positive, that doesn't change our sign. But if I go from a positive to a negative, I'll make a little note here. I varied from this term to this term. So we're really looking at how many times I change from negative to positive or positive to negative. So I went from positive to positive, don't count that. Positive to negative, I would count that. So we say possible positive zeros. We're going to write 1. Only one of these zeros for this function could be possibly positive. Now in terms of possible negative, we haven't looked at that example yet. We're going to look at that next. For this one over here, let's look at possible positive. Possible positive roots. We said looking at the function, we're looking for variations in sign from left to right. So it's in standard form here. It has to be written in standard form, but as long as it's in standard form, I notice I went from a positive to a negative on my first term to my second term. So I'm going to make a little note here. We say we varied in sign there. Negative to positive, we did vary in sign there. Positive to negative, we did vary in sign there. And then negative to positive, we varied in sign there. So we say possible positive, we have 4 variations in sign. I'm going to write 4. So here's where this or is less than that by an even number comes into play. If it doesn't have 4 positive zeros, then we could say it could have 4 or less than that by an even number. We'd say or 2 or 0. So when it comes to listing these, we could have said possible positive over here. We stopped at 1 because if I subtract 2 from 1, I get negative 1, and I'm not going to have negative 1 possibly positive real zero of this. But we'd say starting at 4, we'd say 4 or 2 or 0. Those are the possibilities for possible positive. So in terms of possible negative, here's how this works. With possible negatives, we say the number of negative real zeros of f is equal to the number of changes in sign of the coefficients. So same thing we saw up here, but we say of f of negative x, or is less than that by an even number. So to check for possible negative, I'm going to rewrite this down here. We say f of x on our first function here was x cubed plus 9x minus 25. And when we plug in a negative x, what this means is we're going to do this. We're going to go find f of negative x. And what we find out is everywhere we see an x, we're going to go plug in a negative x. We're going to go plug in this value here, just like we'd plug in a number. So you'll notice that negative x to the third power, anytime you take a negative times itself an odd number of times, it becomes negative. So I really just get negative x cubed. Over here, negative x to the first power, that would still be negative. So we say a positive 9 times a negative x is a negative 9x. And then we say negative 25. When I plugged in a negative x, it was not affected. So we say f of negative x equals this. What we're going to do is go count the variations in sign here. And so it went from negative to negative, negative to negative. As a matter of fact, it never varied in sign. So what this means is, with this function right here, none of its zeros can be positive or possibly negative. They can't be negative. None. None of them can be negative. So now looking at this other function over here, we say f of negative x. We would get this. We get 3 times x to the 4th minus 7 times x to the 3rd plus x to the 2nd minus 13 times x plus 8. And you'll notice that everywhere I see an x, I'm just going to go put in a negative x. So in this instance, a little bit different this time. We'd say Negative x to the fourth. Anytime you take a negative times itself an even number of times, it comes out to be positive. So we get positive 3 times positive x to the fourth. Here we are to an odd exponent. So we have a negative x cubed times a negative 7 is a positive now 7x cubed. Because we're squaring this negative x squared, we get a positive x squared. Negative times a negative here gives us a positive 13x, and then we have plus 8. So this is our f of negative x. All we're going to do now is go back and count variations in sign. So I notice it goes from being positive to positive to positive to positive to positive. So what this means here is this could have no possible negative roots because f of negative x never varied in sign, just as this first one here, f of negative x, never varied in sign. So what Descartes' rule of signs does is it narrows down from your list of possible rational roots how many of them could be possibly positive or negative. If I were to actually go find the zeros for both of these functions, I would say on my list of possible positive or negative rational roots, I would say cross off the negatives because only positives could exist.